Welcome to the world of chip design. In this video, we'll explore the fundamental concepts that drive the creation of microchips, which power everything from smartphones to supercomputers. Chip design is a fascinating blend of engineering, creativity, and precision. We'll start by understanding what a chip is, why it matters, and how the design process begins. Whether you're a student, an enthusiast, or a professional, this journey will help you grasp the essentials of chip design and its impact on modern technology. Let's dive in and discover how these tiny marvels shape our digital lives. Chip, also known as an integrated circuit, is a small piece of silicon that contains millions or even billions of electronic components. These components work together to perform complex tasks, such as processing data, storing information, or controlling devices. Chips are the brains behind modern electronics, enabling everything from simple calculators to advanced artificial intelligence systems. Understanding what a chip is lays the foundation for appreciating the intricacies of chip design. In the next scene, we'll look at the basic structure of a chip and how it's built. Structure of a chip is like a miniature city, with interconnected pathways and functional blocks. At its core, a chip consists of transistors, resistors, capacitors, and other elements arranged in a precise layout. These elements are grouped into modules that perform specific functions such as arithmetic operations or memory storage. The layout is carefully designed to optimize performance, power consumption, and reliability. By understanding the structure, designers can create chips that meet the demands of modern applications. Next, we'll explore the materials used in chip manufacturing. Silicon is the primary material used in chip manufacturing due to its excellent electrical properties. Other materials, such as metals and insulators, are also used to create connections and isolate different parts of the chip. The choice of materials affects the chip's performance, durability, and cost. Advanced chips may incorporate new materials to achieve higher speeds or lower power consumption. Understanding the role of materials is crucial for chip designers as it influences every stage of the design and manufacturing process. Next, we'll discuss the design flow in chip creation. Chip design follows a structured flow, starting from conceptualization and ending with manufacturing. The process begins with defining requirements, followed by architectural design, logic design, and physical layout. Each stage involves specialized tools and techniques to ensure accuracy and efficiency. Designers must balance performance, power, and area constraints while meeting deadlines. The design flow is iterative, with frequent reviews and optimization. Understanding this flow helps designers navigate the complexities of chip creation and deliver high-quality products. Next, we'll look at the architectural design phase. Architectural design is the first major step in chip creation. Here, designers define the overall structure and functionality of the chip. This includes deciding how many cores, memory blocks, and interfaces the chip will have. The architecture must align with the intended application, whether it's for a smartphone, server, or IoT device. Designers use block diagrams and specifications to communicate their vision. The architectural design sets the stage for detailed logic design, which translates the high-level plan into specific circuits. Next, we'll explore logic design. Logic design translates the architectural plan into detailed circuits and connections. Designers use hardware description languages like Verilog or VHDL to describe the chip's behavior. This stage involves creating modules for arithmetic, control, and memory functions. Logic design is critical for ensuring the chip operates correctly and efficiently. Designers simulate their designs to catch errors and optimize performance. Once the logic is finalized, it moves to the next stage, physical design, where the circuits are mapped onto silicon. Let's see how physical design works. Physical design is where the abstract circuits become real. Designers create layouts that specify the exact placement of transistors, wires, and other elements on the silicon wafer. This stage requires careful consideration of timing, power, and area constraints. Tools like place and route software help automate the process, but designers must still review and optimize layouts for manufacturability. Physical design bridges the gap between logic and manufacturing, ensuring the chip can be produced reliably. Next, we'll discuss verification and testing. Verification and testing are essential to ensure the chip works as intended. Designers use simulation tools to check for functional errors, timing issues, and power consumption. Physical prototypes may be built for further testing. Rigorous verification helps catch bugs early, saving time and money in manufacturing. Testing continues after production, with chips undergoing quality checks before reaching customers. This stage is crucial for delivering reliable products. Next, we'll look at the importance of design tools in chip creation. Designers rely on specialized software tools to streamline the design process. These tools include simulators, layout editors, and verification platforms. Popular tools like Cadence, Synopsys, and Mentor Graphic provide comprehensive solutions for every stage of chip design. Using the right tools improves productivity, accuracy, and collaboration among team members. As chips become more complex, advanced tools are essential for managing large designs and ensuring quality. Next, we'll explore the role of teams in chip design. Design is a collaborative effort involving engineers, architects, and testers. Teams work together to solve complex problems, share ideas, and review designs. Effective communication and coordination are vital for success. Each member brings unique expertise from circuit design to software development. Teamwork accelerates innovation and helps deliver high-quality chips on time. In the next scene, we'll discuss the challenges faced by chip designers. Designers face numerous challenges, including tight deadlines, complex requirements, and evolving technologies. Balancing performance, power, and cost is a constant struggle. Designers must stay updated with the latest tools and techniques to remain competitive. Overcoming these challenges requires creativity, persistence, and teamwork. Successful chip design is about finding innovative solutions and adapting to change. Next, we'll look at the importance of power efficiency in modern chip. Power efficiency is a key consideration in chip design, especially for mobile and IoT devices. Designers use techniques like clock gating, voltage scaling, and optimized layouts to reduce power consumption. Efficient chips extend battery life and reduce heat, making devices more reliable and user-friendly. Achieving power efficiency requires careful planning and testing throughout the design process. Next, we'll explore performance optimization strategies. Optimizing chip performance involves maximizing speed, minimizing latency, and ensuring reliable operation. Designers use advanced techniques like pipelining, parallelism, and cache management to boost performance. Simulation and benchmarking help identify bottlenecks and guide improvements. Performance optimization is a continuous process, with designers refining their designs to meet demanding applications. Next, we'll discuss the role of memory in chip design. Memory is a critical component of chips, enabling data storage and retrieval. Designers choose between different types of memory, such as SRAM, DRAM, and flash, depending on the application. Memory design affects speed, power, and cost. Efficient memory management is essential for high-performance chips. Designers must balance memory size, access speed, and reliability to meet requirements. Next, we'll look at interfaces and connectivity. Interfaces connect chips to other components, enabling communication and data transfer. Common interfaces include USB, PCIe, and Ethernet. Designers must ensure compatibility and reliability in their interface designs. Connectivity is vital for modern devices, allowing chips to interact with sensors, displays, and networks. Well-designed interfaces improve user experience and device functionality. Next, we'll discuss security considerations in chip design. Security is increasingly important in chip design, as chips handle sensitive data and control critical systems. Designers implement encryption, secure boot, and hardware protection to safeguard against threats. Security features must be integrated without compromising performance or power efficiency. Ongoing testing and updates are essential to address new vulnerabilities. Next, we'll explore the manufacturing process for chips. Manufacturing is a complex process involving photolithography, etching, doping, and packaging. Silicon wafers are processed in clean rooms to create intricate circuits. Manufacturing requires precision and quality control to ensure chips meet specifications. Once manufactured, chips are tested and packaged for use in devices. The manufacturing process is constantly evolving to support smaller, faster, and more efficient chips. Next, we'll look at packaging and integration. Packaging protects chips and enables integration into electronic devices. Designers choose packaging types based on size, thermal requirements, and connectivity. Integration involves mounting chips on circuit boards and connecting them to other components. Proper packaging and integration ensure reliability and performance in real-world applications. Next, we'll discuss testing and quality assurance. Testing and quality assurance are vital for delivering reliable chips. Designers use automated test equipment to check for defects and performance issues. Quality assurance involves rigorous standards and certifications. Chips that pass testing are ready for deployment, while those that fail are analyzed for improvement. Continuous testing ensures chips meet customer expectations and industry standards. Next, we'll explore trends in chip design. Chip design is evolving rapidly. Driven by advances in artificial intelligence, 5G and IoT designers are creating chips with higher speeds, lower power, and greater integration. Emerging trends include 3D stacking, heterogeneous integration, and custom accelerators. Staying updated with trends helps designers remain competitive and innovate. Next, we'll look at the role of artificial intelligence in chip design. Artificial intelligence is transforming chip design, enabling automated optimization and intelligent verification. AI tools analyze designs, predict errors, and suggest improvements. Designers use machine learning to accelerate simulation and testing. AI-driven chips power applications like autonomous vehicles and smart devices. Integrating AI into chip design streamlines workflows and enhances performance. Next, we'll discuss the importance of scalability. Scalability is crucial for chips used in diverse applications. Designers create scalable architectures that can be adapted for different devices and workloads. Modular design and parameterization enable easy customization. Scalability ensures chips remain relevant as technology evolves. Next, we'll explore the importance of reliability in chip design. Reliability is a top priority for chip designers. Chips must operate correctly under various conditions including temperature, voltage, and stress. Designers use redundancy, error correction, and robust testing to ensure reliability. Reliable chips are essential for critical applications like medical devices and automotive systems. Next, we'll discuss the importance of cost optimization. Cost optimization is vital for making chips affordable and competitive. Designers balance performance, power, and manufacturing costs. Techniques like design reuse, process optimization, and efficient layouts help reduce costs. Cost-effective chips enable widespread adoption and innovation. Next, we'll look at the role of standards in chip design. Industry standards guide chip design, ensuring compatibility and quality. Designers follow standards for interfaces, testing, and manufacturing. Standards promote interoperability and simplify integration. Adhering to standards helps designers meet customer and regulatory requirements. Next, we'll discuss the importance of documentation. Documentation is essential for successful chip design. Designers create specifications, design notes, and test reports to communicate ideas and track progress. Good documentation ensures clarity, reduces errors, and supports collaboration. It also helps with troubleshooting and future improvements. Next, we'll explore the importance of continuous learning. Chip design is a dynamic field requiring continuous learning and adaptation. Designers stay updated with new tools, techniques, and trends through training, conferences, and research. Continuous learning fosters innovation and keeps teams competitive. Next, we'll summarize the fundamentals of chip design. We've covered the essential concepts of chip design, from structure and materials to design flow, teamwork, and trends. Understanding these fundamentals equips you to appreciate the complexity and creativity involved in chip creation. Whether you're pursuing a career or simply curious, chip design is a field full of opportunities and challenges. In our final scene, we'll reflect on the impact of chip design on technology. Design has revolutionized technology, enabling advancements in computing, communication, and automation. The chips we design today shape the devices and systems of tomorrow. As technology evolves, chip designers will continue to innovate and solve new challenges. The fundamentals we've discussed form the foundation for future breakthroughs. Thank you for joining this journey into chip design fundamentals. Stay curious and keep exploring the world of microchip.